So today we'll talk about the tiny URL, and we'll talk about the whole system iteratively, like how you would go about doing this if you got this on an interview, right? So let's start. So the question if the interviewer says, okay, let's design the tiny URL. So the first thing we ever start with is gathering all the requirements. Okay, so we'll ask them, what does this system entail? What does this do? Okay, so for those of you who don't know, the tiny URL is like an application in which you have, like you put in a long URL, say strava.com / whatever 1212, and you say generate. So it takes in a long URL and it converts it to a short URL. Okay, so we can call this, like, you can get tiny URL / 123. Okay. Other things we could talk about is we can do the reverse, right? We can reverse it is like you give tiny URL / 123 and then you expect to get back the Strava URL that you put in earlier. Okay, so it is two steps. One is long to short and short to long. Apart from this, we can think of other questions like, okay, what all functionalities do you want me to have in this application? How are people interacting with this API? So we thought about this was first case, the second case, third question could be, do we want this short URL for some time? So do we want this time to live for the URL that we just created? Do we want to monitor analytics on this? Like how many people, number of people interacting with it? Do we want to keep like geographical location for where the user is when they interact with this API or they ask for this particular thing? Do we want to give like custom links, like, oh, instead of having this random Strava 1, 2, 3, 4, we can have our own, like say tiny URL Shivi. Okay, so then instead of giving us giving them a random tiny URL, they can make their own. Okay, so given of that, if they can customize the link and they customize the TTL. Okay, so you can talk about all the features that you think you want to build. Okay, so then the interviewer will guide you that, okay, let's talk about just this portion. So for the sake of this video, I'm going to talk about the first one, which is where the URL, when you give the big URL and you get the small URL back, and then the vice versa, where you get the short URL and get the big URL back. And maybe a little bit on the analytics. We'll keep this, we'll see. Okay, so once we have this down, we can talk about the short URL. Okay, the URL would look something like this. So if you give in the big URL, you want to get something like this. Okay, so this part is something that should be unique so that we can differentiate between, say, URL1 versus URL2. Okay, so first thing is we can randomize it, random unique. Okay, for say URL1 and then same for URL2, and then we are assuming there'll be no or less random collisions. Okay, but just imagine of this, if URL1 is the same, URL2 is the same, maybe we can give the same URL, short URL just to save on space, right? Other thing we could do is we can take the URL, for example, in our case it was Strava, right? Strava.com / 12121, and we can do an MD5 hash. So you want to use, like, I want to design a function or a hash in which if you give X, I'll always get Y. Okay, so find the MD5 sum and then I extract some characters, n characters, and work with that. Okay, so this MD5 sum will always give me the same thing for the same input. Okay, so for example, in our tiny URL, let's suppose we want to use 7 characters, 1, 2, 3, 4, 5, 6, 7. Okay, so I'll take the MD5 sum value and then I'll just use last 7. Okay, characters. So this way, whenever I give strava.com, I always get the same thing. So let's define what the short URL will look like. So the short URL looks like tinyurl slash some 7-character generated by the MD5 sum. And what do we assume the characters would look like? The characters would range from, say, 0 to 9, small a to small z, capital A to capital Z. So in total, it looks like we have 62 different characters, and because the length of the string is 7, we can form 62 raised to power 7, that is approximately 3.5 trillion unique strings. So additionally, tiny URL is 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 7 equals to 15 characters, and each character is 1 byte. So 1 is to 15 bytes. So 15 bytes for storing 1. So you can see over here that this application is read heavy. Like similarly for Instagram, right? Do you post more than you see, or do you post less? If you're not a content creator, it's highly likely that you're posting less and reading more. Let's talk about the basic API we are supporting. So we're supporting 2 APIs. One is generate the short URL, and the second one is short to long. Just to mention that we're going to use this more often. Okay, so this is going to be the heavily used API from our discussion before. Okay, so we can think about storing the data in a database like a random ID, long URL, short URL, time to live, visited. Although we're not discussing the time to live right now, I'm just giving you an idea of what the database would look like. Now, coming back to this question, we talked about how we'll generate the URL. We said that we'll use the MD5, we'll use the last 7 characters. So there could be cases in which there would be an overlap. Okay, so there would be cases in which, let's say, f Strava gives 1 2 1 2, and f Fitbit gives 1 2 1 2. Okay, so how to deal with unique short URL collisions. Okay, so what happens is, given the MD5 function, 2 of the inputs, or 2 long URLs, are giving us the same short URL. Okay, so from what we know, how do we handle collisions? There are 2 ways to handle collision that we know of. One is chaining, and the other one is probing. Okay, so in chaining, it's like, okay, so at 1 2 1 2, we can just add Strava, and if we see Fitbit and has the same 1 2 1 2, then we just add it as Fitbit. Okay, but in databases, we can't do this, right? We can't do this in databases. So what do we have to do is probing. What is that? So now, supposedly, if f Strava comes first, it finds itself as 1 2 1 2, and then in the database, it would look like this: 1 2 1 2 Strava. Now, when f Fitbit comes, it sees that, okay, this is taken, but then the next one, 1 2 1 3, is not taken, so it will add itself there. Okay, it finds the next available. Let's move on to the sequentially and adds itself. So the high level diagram is like, how are we envisioning the whole application? So first, anything would be, you have a user, you have an application, and then you have a database. Okay, this is a very simple view of how any database or any system comes up. And once we start getting more users, we have to think about, as the users increase, the latency increases, the system load increases, the data increases, the data storage increases. So we have to kind of scale our application. Okay, and if you notice over here, if something goes down, we lose everything. So we need to kind of scale most components. Okay, so we'll talk about scaling this whole the simple application and how do we go about it. Okay, one of the ways that I could think about is, obviously, wherever we have single points of failure, it's best to add more resources to it. Okay, so instead of the users talking to one machine, the users talk to a load balancer, okay, which hides behind multiple instances of the application, which further has a bunch of databases that are connected. Okay, applications and databases. And the user talks to this and it can be routed anywhere. So this way, we don't have a single point of failure. Now, when we have multiple systems, the first topic we're going to talk about is replication. Okay, in replication, we can do two types of replication. One is the single, actually not two, there are three types of replication: single leader, multiple, and leaderless. To understand multiple, we'll start with the multiple leader replication and the leaderless application. It means there's no leader. So there's an application and there are people who are kind of interacting with the application. Okay, and they have no knowledge about each other. So this one says Strava. Okay, what are you going with? And it says, okay, you have 1212, and this one says Fitbit. And it says, okay, you have 1212. So there will be a collision. Okay, so how would this handle it? We could handle it by use the last write. But in a single leader application, what happens is all the applications talk to the main leader or like the coordinator, which kind of writes it subsequently to each database. So supposedly consumer 1 comes, consumer 2 comes, consumer 1 wants to write Strava, okay, and then the leader says, okay, you want to write Strava, so then you put a lock on me, so you lock that row and then you take it back, and you can get this 1212, and then you say, okay, Strava. Now when consumer 2 comes, because the lock is with C1 and then it already updates it, when this one comes in, it says, oh, 1212 is taken, maybe I'll give you 1213. So this way, leader manages collision and overlooked overrides are avoided. So given in these two systems, I would personally go for the single leader replication, where I want to avoid when two people get the same small URL, but they point to different things. And if in this case, the consumer one, when they come back to 1212, instead of seeing Strava, they seeing Fitbit. Okay, so I would prefer using a single leader replication database. So in this case, you can use MySQL, SQL, and we cannot use things like Cassandra, which has leaderless replication. Okay, so we can use a relational database with two-phase locking. So when I told you about the lock, this is what I was telling you about, that each consumer will talk to the leader and get the lock before writing into the database. Okay, so coming back to this diagram, there's another improvement we can make. So now the users were like talking to load balancer, and this user is in, say, Australia, and this user in the US, right? So what we can do is to reduce, and depending on where the store or data is stored, we'll have latency. To reduce latency, what we can do is put caches. Coming back to our diagram, so there's a user who talks to the cache, and then the cache talks to the load balancer and the application. Okay. So now when we have introduction of caches, going back to writing, we have three ways in which we can write. Write around, write through, and write back. So in this write through, the person writes to the cache and to the database, or like the next app, the application. Okay, and in write back, it only writes to the cache, and then later on, cache writes to DB. Okay, and in write around, the user straight away writes to the DB, avoiding the cache. Let's talk about the drawbacks or the trade-offs of each. So when I'm writing to cache and the DB, I need locking. It's slower. Okay, and over here, when I write just to cache, cache is in memory or transient, so I might lose it. So we have possibility of losing. Okay, and then over here, there's only one write, so it is faster than 2, which is the write through. So I'm calling this 2 and this is called 3, but it's slower than 3. Than 3. We get the added benefit of persistence. Okay. So in this example, I kind of think, I believe that I would go around with the write around cache. Why? Firstly, it's giving us better performance than the second one, which also gives us persistence, and persistence is important in the application that we are designing. So now we could talk about partitioning the data. So what does partitioning give us is increased throughput, and it's able to better distribute the load. Okay, so we can partition the data, say on the short URLs. Okay, so now when we're looking up something, we're partitioning data. So we store like say A to Z on here, and not A to Z, that would be different. Let's say A to M here and N to Z here. So data is partitioned. So there are benefits to this. There's like, okay, when we are looking for something from say B, we go to this. We're looking for something from O, so it's here. So then the data is partitioned such in a way that when a request comes, the coordinator can say, okay, I'm looking for B, go this way. I'm looking for O, go this way. Okay, so even on after partitioning, we can have an index. So we can have an index, say on the short URL, or like, yeah. So when we have an index, now when something is going for B, instead of going through all the instances, which is log of O of N, we have index, so we can do binary search. So that will get down our search to log N. Okay, so we can have an index. Okay, so within the partition, we can have an index. So if someone says, I want to look for banana, right? So, and we have apple, banana, and say coffee. Okay, so when the request comes, we know this is M to Z or N to Z, and let's say this is on this, we say, okay, now the coordinator is like connected to these two. So now the request comes for banana. I'm like, okay, go to banana. Like, okay, A to M here and N to Z here. So like, okay, go here. So within this, there's an index. So we're like, okay, this is an index. So it is already sorted. I'm looking for banana. So I can do binary search and find banana. So this will be O log N. Whereas if we didn't have the index, it would be O of N. So within indexing, there are 3 kinds of index that I know of. One is the hash index. The second is the B tree, and the LSM tree with SSN table. Okay, so this is the fastest. Why so? This is in memory. So again, this is also limited by memory. Over here, these two are like B tree, if you know, is like a binary search tree, and everything is written on disk, location. Okay, and with this, there's a tree, and there's a table, like a write ahead log or table that keeps in, okay, add apple. Apple is this, remove apple, then like removed. Okay, so there's a tree, there's a log which is in memory. So if we have to write, right, now let's look at this. I'm kind of getting over with this because we're limited by memory, and it's something goes down, the index is gone, right? So my choices are limited to the B tree and the LSM tree with SSN table. So like when we have the hash collision, we need to find the next one, right? find next available position. So this way the next index is on the same node. Okay, and between them this is faster writes and because over here you just need to write to the in-memory table, and over here this is faster reads. And because I want to make this application faster in reading, so I make this a faster reads. So I choose the B tree. Okay, so this is our basic design of the URL without considering the added factors of clicks,